right here. So everything that goes on that screen will be recorded. I would like to invite you, before I start, I'd like to invite you to my LinkedIn. Everybody familiar with LinkedIn? This is the Facebook of the professionals. So please, I'd like to invite you to link with me. All the information about me is on in LinkedIn. You can connect with a lot of people in LinkedIn. If all of us are professionals, this is the Facebook of the professional people. No question asked. So I invite you to link with me. The second thing I would like to show you before I go ahead and start, because I'm not busy enough, I don't know how many of you, I started my YouTube channel 4 years ago, and to date, all my lectures, including this one, will be on YouTube channel tonight. I have close to literally 800 hours of technical electrical. You're not going to see a monkey jumping in that YouTube channel. It's all electrical, technical, engineering, and electrical construction on YouTube channel. I'm a firm believer, like you said, in YouTube channel. I watch a lot of stuff. I learned a lot, and I share my what I know with the whole world. No bragging rights or anything. I've been seen in 196 countries and regions. So isn't that cool? I mean, just to be for an average Joe to be seen, and you get feedback from China and Germany and so forth. So feel free to go there. I have a lot of stuff if you're interested in the electrical business. My YouTube channel is just Chad Kurdi. Here's my last name, Chad Kurdi. One between parentheses, you should be able to go there. I invite you guys to get me some feedback on this. With me today, I have a couple of things, guys. I'm an electrical engineer, so I would like to ask you, how many of you guys are in the electrical field, engineers or electricians? Just to give you an idea. Okay, so that's why you guys are here. Any engineers? Everybody's technician, electrician, engineers, electrical engineers? Okay. So for this is meant not to explain why the wind is important. You guys did a great job. Sustainability, care about Mother Nature, and all this good stuff. We all believe in that. This session is when you decide to put a wind turbine, how do you do it based on the Bible that we have? This is called the National Electric Bible, the National Electric Code. So how do you design a system and install it safely and hopefully economically if you were to decide to put a wind turbine or a solar system? So that's kind of what this presentation is all about. So if there's a few technical stuff, for the non-technical guys, please forgive me for that one. We have the NEC code book. These are the articles that talks about it. I'm going to be going over this article. And I do have a site that I thought for small wind turbine. This little site, a wind spot, is really cool. It gives you some information about small wind turbine. These are not the 2 or the 4 or the 5 megawatt turbines. These are the small ones that the National Electric Code concerned about. You will see. So that's what I have with me, this site for you. And before I go ahead, I have my presentation. If you guys are interested in these, the PowerPoint, I should be able to PDF it to you or email it to you as a PowerPoint. I have no problem with that one. So in 2011, the ones who are electrician here, you're familiar with National Electric Code. It comes every 3 years since 1897. I forgot to tell you, I'm a vivid collector of the National Electric Code. I have a full collection of them until the 50s. I wasn't in the 50s or the 60s alive even, but I collect them anyway. So we have since 1897, the first ever NFPA National Electric Code adopted. Since that day, guys, and in 2011, the cycle in 2011, the NEC code book recognized that wind is here to stay, even though wind has been here for a long time. And we introduced a National Electric Code article to handle how do you install an electrical system safely, So that's what I'm going to go over this article, show you a couple of things, a couple of slides. I feel free, guys, to jump in at any time. So I like your presentation when you guys talk about sustainability. To me, sustainability, electrically speaking, is introducing renewable energy. Renewable energy, one of the major sources of renewable energy is solar, and wind. Fuel cell is another renewable energy. These are the electrically speaking. I emphasize the word electrically speaking. These are the ones that the National Electric Code handle. I picked this one because this brand new article in 2011, I don't know what your states are, but in Minnesota, we adopted the National Electric Code. We always adopt the latest. We jump into the latest NEC code book. So Article 694 talks about small wind electric systems. So these are the ones they're going to handle. A few things about this article, my friends, as if you're not familiar with, it handles one or more wind electric generators. They can look in any shape or form. You look at them. Typically, this is the typical look for these systems, but they're limited. This article covers up to 100 kW. So if you're looking for 2 meg and 3 meg and 4 meg, this article is not for you. You have to have engineered project. And that's where the engineers jump in and size all the system. And if anybody is interested, there's a lot of information about the 2 meg. But this particular article covers the 100 kW or less. And my understanding, the reason for this, because these are the most commonly installed ones by electrical contractors and people. Nobody puts 3 or 4 meg right in their backyard. Anybody? Can you have a permit to get a 4 megawatt turbine in your backyard? The city will probably put you in jail before you put that one. So these are smaller ones. You see them on farms. You see them on people's, if they live in small towns in their backyards and so forth. Typically, these are 60 feet to 100 feet towers. Between 60 to 100 feet, you put them at the top, and they range from a couple of kWs into 25, 30, but the code covers as high as 100 kW. Anybody installed wind here? Installed wind turbines? Okay, so these are, I will emphasize the word, this is limited to 100 kW, this arc. And it includes, of course, the generator, alternator, the inverter, and the controller. You're going to see the interactive system in a second here. We have an interactive system. Those of you who are electrical, you're familiar with an interactive system. This is a live system. You can throw the power on the grid and send it all the way to Minnesota from here. That's my interactive system. You can have standalone system. If you live in the Smoky Mountains here and you decided to go off the grid, that could be an option for you too. And the output of this system can be AC or DC. Most of the utilization equipment that we use, electrically speaking, are AC, but you can also utilize electrical equipment at the DC level. You can have batteries or not, it's up to you, so it can come up with a battery backup or not battery backup. So that's kind of an overview of the whole system. The ones who install solar, if you guys are not familiar with the wind, this is very similar to the solar. This picture is actually very, very similar to the solar system. The small wind comes with your alternator over here, and because we use the wind to drive the alternator as your prime mover, and unlike diesel engine generators, recognizing my friend from a long time ago, unlike diesel engine generator, we can control the speed of a motor, and by controlling the speed of the engine, you can control the frequency. The most important thing is to maintain the frequency, otherwise you'll burn equipment. You cannot control the frequency a whole lot for the alternators. So most of small ones, what they do is they take whatever the Lord give you, wind and speed wise, and whatever frequency comes out of here, and they rectify it to DC. Now you capture it at the DC level, then you invert it at the right frequency, at the right voltage, and you throw it at the grid. So that's very, very important with a small, because you cannot, typically controlling the speed of the wind is not non-controllable item, right? From a design point of view. And there's a lot of things, guys, how to solve the speed of the wind in order to control the frequency of the alternator. And if you're in the electrical field, engineers and electricians, you fully understand what I'm talking about, the frequency over here. So what they do is they alternate, they take it, and they have, so whatever frequency I like to draw, I don't know if you guys, the trainers will probably like this function here. So whatever frequency you come over here, when you come out of the DC, you rectify it, it becomes DC, and right here, like nice smooth sinusoidal wave. For non-electrical people, who cares? You don't burn equipment, right? Does that like a wind? So that's the most important thing. So this is the major component of a wind turbine. This is so-called interactive system. Interactive system means you generate and you throw at the grid, and other people or you can utilize this power. The second system that they have over here, that's called the standalone system. A standalone system, you live in the boonies and you want to get off the grid. You can have a solar system or you can have a wind system. So the same thing, you have to have your alternator, get you whatever frequency you get, you rectify it. With this system, You need a charge controller, because you need to store the energy a little bit, right? If you're off the grid. If you're on the grid, you throw whatever extra you have on the grid, and somebody else will utilize it. Here, typically you have the charger, you charge your battery, you have a diversion load as part of your control of your alternator. And then at this point, you can utilize, meaning you can put a fridge that runs at DC, or you can invert it back and run a fridge and a light that runs at AC. So you have two options here, utilizing at the DC level or at the AC level. So that's kind of the block diagram of solar photovoltaics, of a wind turbine system. Any comments, guys? Any questions? Please jump in at any time. Correct me if I'm wrong. Do I have a what? I'm sorry?
Do they have to have the diversion load?
There's so many. Diversion load is used to, we'll talk about this one in a second, used to control the charging of your battery, and also as part of controlling your alternator. Controlling the alternator. For example, if you have a big gust came, and you're going to get rid of that huge energy that generated, my understanding is you dump this, it's just a bank of resistors. You dump that extra energy into the diversion mode to control your system. So as part of your control of your alternator, and there's so many alternator, guys. The bigger ones don't need that one, but you need that one as part of your controlling charging the batteries, as well as your alternator, as your alternator. If you have a grid, you can throw that extra on the grid too. Any comments, guys, about this block diagram before I move into a couple of little details? For those of you, I did this presentation the year before, by the way. I think you were in that presentation. This year I submitted two. I wanted them to pick up the medium voltage. Anybody likes medium voltage? Medium voltage system higher than 600 volts, but they picked that one. So you guys you're stuck with listening to the same presentation. Okay, here's a block diagram. For those of you who have not seen that, probably this slide, guys, summarizes the whole article, really, from my point of view. This particular one slide summarizes the whole article that talks about wind. So you start from number one right here. This is your nasal. That's where you put your alternator and control circuit. So you have that wind turbine over here driving your alternator. So you might have some gear over here, and you have some control circuit. So that starts right in here. You get your wind. That's your so-called prime mover. We call them prime mover. So your prime mover here is the alternator. Your prime mover is the wind, and drive your alternator, and that's where you generate right at this level. So that's ground zero for the power. You capture that power. You put it, of course, as number two is you need to raise this one on a tower so you can make it more efficient, capture more wind to get more, the optimum design for this wind. The tower, so you get down here, you have your tower. Like I said, typically 60 to 100 feet. You throw that nasal at the top of 60 to 100 feet tower. When you put it, just to mount it physically, mechanically, hold the nasal. Then right underneath it, so you bring your wires from here all the way down through this tower. When you come over here, and these are all required by code. Now, electrically speaking, you're going to have the tower grounding. We have to have some type of a tower grounding over here. And the code requires you to drive a ground rod, one option, to have a so-called, and this is technical terms, I apologize for non-technical people, it's called grounding electrode system. You have to provide a grounding electrode system, nothing but other than a fancy name for a ground rod or a concrete encased electrode, rebars. So any metallic object in a proper contact with Mother Earth, we call it.
You can grab it to the rebar in the foundation?
Absolutely. If it qualifies, yes, absolutely. Concrete encased electrode. That's what rebar is. So if you have a foundation over here properly grounded, concrete encased electrode, in direct contact with Mother Earth, that will qualify as your, this number two is called grounding electrode system. Grounding electrode system, a ground rod or the concrete encased electrode, rebars of the foundation. So that's number two, ground, and we use the term grounding electrode system and grounding electrode conductor. So you have the system, and you tie the tower into that grounding electrode system. And sometimes the bolt themselves actually act as your grounding electrode conductor. Any comments, guys? Bringing the power from here through the wires down. You have to ground the wire, and one of the most important reasons why we ground the wire is, of course, they call it auxiliary grounding electrode system because of lightning. Like any other generator, the code require you, even if you have a generator outdoor, to have a grounding electrode system right by the generator. So this is really nothing fancy. This one could be single phase or three-phase system. It doesn't really matter. As far as generating, you can generate the single phase system or you can generate a three-phase system. Typically three-phase system when you generate. But the whole sizing, it really doesn't matter. You still, if you put a single phase turbine here or a three-phase turbine here, the sizing is obviously the current is going to be different, but the sizing will be the same. Any comments, guys, about this one? So we grounded the tower for lightning and stabilizing the system. Then you go number three here, they call it Turbine Output Circuit. Turbine Output Circuit, and I did a couple of calculations. These are all from NEC code book, not to overwhelm you there. I have a couple of slides from that. So when you bring the wires here, typically your three wires coming from the turbine into your disconnect, these need to be sized. You guys are all electrician engineers. When we size any system, if you don't know how to size a conductor, just use the word 1.25. And you are 90% of the time right. 90% of the time right if you say 1.25 for any sizing of conductor. And by the way, even overcompression device, if you say 1.25, 90% of the time you're also right. So remember that word, 1.25, 25% extra. So they put 25% extra for safety on it, and they size your conductors. And that would be the cables coming from the turbine down into the first disconnect means. And then we go to number 4. What I like about this slide, guys, it's because it's numbers, it's easy to follow the whole system. Then you bring it into the disconnect. This number 4 is the tower disconnect. The tower requires disconnect with some exception. There are exception for this one though. You require a disconnect. We're all familiar with the disconnect. Simultaneously disconnect all the ungrounded conductor from the turbine. So your disconnect, number 4, how do you size the disconnect? Remember that 1.25, that magic number that worked for everything else? You take the I maximum, the way they get the I maximum, so you get your turbine, say your turbine is 7.5 kW, and your voltage is 3-phase 220. Come in, so you take the kW divided by 1.73, 220, assign a 0.9 for power factor, you find your amps of that turbine, you multiply by 1.25, you size the conductor. They call it I maximum. The I maximum defined in the code as the maximum current that this unit will generate at a speed of 25 miles per hour. That's kind of the speed that they use to generate the maximum current. Okay, so we got the conductors to land into a disconnect for safety. If you disconnect it, right next to it, SPD, surge protective device. You guys are very familiar with this one. We're very close to Mother Earth. Lightning is a big option here. What happens if you get hit by lightning here? You're going to burn some equipment. Worse than burning the equipment is that lightning surge is going to go right through your disconnect, right through your building, and burn the building wiring system too. It's not enough that burned your tower, now you burn your wiring system. So the smarter than Chad, I always say, number 5 will be so-called surge protective device. We'll talk about this one, guys. I have a couple of details about it. Surge protective device. The ones who are familiar with it, these are 3 types, type 1, type 2, type 3. Type 1, you put it in the line side of a disconnect. Type 2 on the load side of the disconnect. And type 3, you put it right where the outlet behind you, right there, in one of these outlets. Type 1 being the most robust, and type 1 is the most robust, and type 3 is the least robust in terms of handling the surge. So that's my surge protective device. Any comments, any questions about surge protective device? Straightforward. Moving into from the surge into now here, we get, like I said, up to this point, you're going to be getting whatever voltage, like we said over here. Then we get into also the rectifier. So that voltage have to be rectified because you put this one in your fridge, you just burned your fridge, literally. So you need to rectify this voltage. You have to bring it to the rectifier. Like I said, your rectifier really nothing but grabbing it into rectifying it into a DC line. And then here, look how nice, I don't know how nice is that one, but here's where you get your nice so-called sinusoidal wave. So first you take whatever voltage and frequency you get out of this unit. You bring it to the rectifier. The reason for it, because you will control the frequency, right? You get to control the frequency by converting into DC. These are bridges, typical like you do in your my laptop right now. We're taking AC, converting it to DC and dumping it. So rectifying it. At this point, you bring it back into from rectification. You invert it back to AC because most of the loads that we use AC. You dump it into the grid. The code requires you to have also a disconnect. And these are very important for us guys when we size for electricians. Again, electrically speaking, I apologize for those who are not electrical. The code requires you to have a disconnect on the load side of the rectifier. The DC, this side, this is the rectifier has to have its own disconnect. Now, if the rectifier is within sight of the tower, the same disconnect can be acted as a disconnect for the tower and a disconnect for the rectifier. So there's a few things here, but say if they are inside, indoor, you have to have a disconnect for that rectifier. Then typically these two units are side by side, and you have to have also a disconnect for the inverter. So these are typically one unit, and you have to have a disconnect for the inverter on the AC side. Okay, so we get into number 6, guys. Rectifier inverter disconnect. That's this one. You take Imax, the maximum input of that rectifier, which is typically matches the maximum input of your unit, and you size your disconnect. Rectification, just to get you the DC, that's number 7. We're moving into number 8, guys. You have the over voltage protection and load load. These two are part of controlling your gust. You get a big gust over here, big voltage, big current came out of it. Instead of dumping it in here, you can diverge it as part of your control of your turbine. So you can dump it through a bunch of resistors and burn the energy. So that's your number 8, so-called diversion load controller and over voltage protection from gust. I just added here from gust. And the resistor is nothing other than it sees a higher voltage, higher amps than it can handle. It diverges it directly and burns it through these resistors. So that's your rectifier, inverter disconnect, rectifier, diversion load. Moving into number, so inverter, then you get into number 10 here. That's the DC line. That's your DC line. So that's the same thing, the output of the inverter multiplied by 1.25, and you size the overconduction device as well as the conductor. Remember that, the magic word, 1.25. So you size your conductor, that number 10 here. You bring your conductor into number 11, the inverter, the interactive inverter. Now you invert it back to AC. You need to bring a bunch of conductors here, typically 3 conductors for a 3-phase system, or 2 conductors for a 2-phase system. And you multiply it by 1.25, and you size your conductor as well as your overconduction device, which acts also as your disconnect. So that number 13 acts as your overconduction device, so-called overconduction device, as well as your disconnect. So that's basically the block diagram and the sizing for the whole wind turbine. Any comments, guys? Any questions about that? Any comments? Any questions? Straightforward? No? Yes? More? Part of so rectifier, inverter, and voltage, these can be 2 separate units or 3 separate units or 1 unit. There's technology that inverter, rectifier, one big unit that inverter, rectify, or it could be 2 different units with the over voltage protection as part of your rectification system.
The rectifier gets rid of the voltage fluctuations. Your AC voltage fluctuations, when they get the rectifier, they're gone.
They're gone.
You've got a flat DC voltage.
Absolutely.
Okay.
Yeah. This is not really for an over voltage. This is for the over voltage protection that's coming out of a gust, not normal operation over voltage. So you have a big gust come in, and for a short amount of time, you over voltage and you have more current, more power than the system can handle it, diverge it right directly in, and burn it through these resistors.
Essentially, you rectify an inverter and make what you find on VFD. You can come in and input on.
Yeah, typical, like VFD, thank you. VFD is a very good example of taking rectification. Yeah, taking an AC here, an output AC, input AC, output AC. Instead of doing speed control here, they're really, yeah, they're just converting it to control the frequency in this case. Yeah. So this is a good application. You put the two together and get your VFD control. Good point. This is an interactive inverter, as you mean synchronous as an interactive inverter. This is, yeah, synchronizing with the grid. There's a synchro. Okay, this will be interactive if you have a grid. In this case, we do have a grid. This has to be interactive in inverter. And that's where we're getting into the detail now. If you dump the power into the grid, they require you to have UL listed interactive inverter like they do in the solar system. When you have interactive for a solar system, the same way. You have to have a UL listed.
They call it anti-islanding.
Absolutely. So you have to have the same requirement, anti-islanding. So that inverter here will be monitor the grid, and if the grid is down, and there's another technology, the actual diversity. If the grid is down, your system is down. But there are inverters that if the grid is down, it will isolate the grid and connect you directly to another load. So it acts as a backup power, basically. So, but you have, if you're dumping on the grid, you have to have an anti-islanding. Anti-islanding, it doesn't mean you dump your load. It means you isolate yourself from the grid. Now, what do you do with the power is up to you. So if your inverter is capable of, and there are some of them right in here, diverging that load into, so rectifier inverter right here, you isolate your system here and you diverge this load into another panel and utilize it internally, that will meet the anti-islanding. As long as you isolate yourself from the grid. Transfer switch, or there's an inverter that has, I've seen an inverter where yeah, just divert you to another set of contacts, take you to a separate panel that feeds a separate load in your building. With the manual or auto transfer switch, yeah, because these loads cannot be connected to the two sources at the same time.
SMA does that.
Who?
SMA uses two different inverters, and they'll trick the grid tie with the other inverter, but they can still connect it to the grid.
Why would you do something like this? Is that?
I don't know if my
Yeah.
son did it, so I was just curious as to what he thought of it.
So you are connected to the grid even when you are lost, when you lost power. That's against the code. If you
Where's Nebraska?
so if you you know what the idea, would the system work? Definitely. Would it work? The whole idea of anti-islanding is if the grid is down over here and they're working on these lines, the transmission guys, and you are pumping power into these lines, you could kill, well, actually you're not going to kill them. If you do medium voltage, they do it completely differently, but they don't want you to do it anyway. When they work on these lines, guys, by code, by high voltage code, they have to ground them and shunt them to the ground here. So even because they don't trust you, you think they're going to trust you even in Nebraska? So that the utility people, when they work on these lines, before, based on OSHA rules, before they even touch them, they have to identify, first, measure that there's no voltage across them, and second, with their gear, they have to put these bonding jumper here, bond all the phases together, take it to the ground. So they will short your system and your circuit breaker, he will trip. So to protect themselves still. But you still have to have the isolation. Any comments, guys? Any questions about that one? So that's kind of in the whole. I'm going to watch my time here. So that's basically the whole view. Here's another system, and I grabbed these ones. There's so many technologies, guys. The same technology. My understanding that the way they use this system is they can't find an inverter that can invert all the power that's coming out of this turbine. So they need, so what they do is multiple inverters. They kind of slice it into 2/3. They take the power here because it's bigger than what one single inverter can handle. So they take it over here, they collect it into a panel. That's easy, right? You collect it into the panel, split it into 3 chunks, 1/3 each, land each third on one inverter rectifier system, and then bring it back into the AC as a three-phase system, like you can see. So why would you do something like this? Because you utilize the available inverter size-wise. Any comment, the same system, except you can see that they're splitting the load into thirds. So if that was 6 kW, you will have 2, 2, 2, easy to invert and convert, and bring them back here, parallel them again, and feed as a three-phase system. Feed as a three-phase system. Any comments about this? Anybody install a system like this? No? System like this. So that's what I have for you. I'm going to tell you guys this is a 2-hour presentation. So when we reach 3 o'clock here, I'll let you guys go. But then I went through here and I just sliced the whole stuff that we defined at the beginning here, just to go through that a little bit more details. Go back, Chad here. There you go. So all these numbers, guys, now there's a lot of details. Like they say, the devil in the details. So here's the definition of the first thing they define all the stuff. So we have charge controller. Here's what talk about a controller. Controls the DC voltage and or current and charge the energy storage device, aka the battery. So that's what the function of the charge controller. We all know that. Diversion controller, charge controller regulates energy storage, the battery's charging process by diverging the power from the energy storage to the DC or AC load or to the utilities. So that's your diversion load as part of controlling your battery if it's existing, and or part of controlling the speed of your turbine. Diversion load, nothing but a bunch of resistors that you can burn the equipment through them. Diversion load connected to the diversion charge controller or diversion load controller, the charge or the load controller, as part of controlling the batteries, regulating the voltage of the batteries or the output of the turbine. And this is where the diversion load controller regulates the output of the wind turbine by diverging the power away from it upon the existence of a gust. So I went through these ones. And then, of course, you have a tower. So you want to put a tower. There's so many ways of putting a tower, guys. Some towers require you to have a guy. Others don't. So if you have a guy, they define what the guy is. All the electrical utilities define the guy all the time. So cable mechanically supports wind turbine towers. That's my wind turbine tower. And then they go and define all these output circuits. So this is how they define the input, the inverter output circuit that's coming out of the inverter when you say. So these are the conductors between the inverter and the AC panel for standalone system, or between the inverter and the utility if it's not a standalone system. The maximum, maximum output power, they define it as 1 minute average power output when turbine produces its nominal steady state operation. So to get into the definition of the maximum power and the inverter circuit. That helps a lot when you size all these systems. What I did, like I said, if you guys want this PowerPoint presentation, I put these number 12 here is related to the graphic in the graphic that I showed you. So it's kind of tie the ones that at least tie directly. Here's how they define the maximum power. There's a few definitions here. The maximum voltage wind turbine produced in operation, including open circuit voltage. So when you have an open circuit voltage, it will be higher. They define the nozzle over here. It houses the alternator and some control system for it. Rated power, I thought it's really interesting. This is how they define it. The rated, when you have a turbine of 7.5 kW, it's defined at this speed, the optimum speed of 24.6 mile per hour, or 11 meter per hour too. So that's how it's defined. Now and then they tell you, you're familiar with the code, the electricians among us, the NEC code guys, there's always a rule and there's what? 5, 6, 7 exceptions. Right? So the rule is how defined, and they tell you, by the way, if you have a turbine that can produce more power at lower speed, stick with that more power. So, and then they refer you to the IEC standard that talks about measurement of energy production turbines. So I thought if anybody teaches this, there'll be a nice slide to walk them. So this is walking the people through the article that talks about wind. And the reason why I picked the wind and sliced it more is because it's brand new article in 2011, just came in 2011, so brand new for us. The tower, the pole or the structure that can be any type of structure, a structure that supports wind turbine. Wind turbine, mechanical machine that convert energy, back to what you guys said, wind energy into electrical energy. So it takes the wind energy, convert it to mechanical energy first, and back into electrical energy. So, you know, there's so many technologies, guys, and if you go through, I have a book about calculating how much energy comes from the wind to how much energy you can utilize there. There's a lot of losses involved in the conversion from wind into mechanical, number one, and in mechanical into electrical, number two. So luckily, we don't get involved into a whole lot of this. We take it as here's the power that we have, the maximum power, and go size the system for us. And there's an optimum design and optimum height for these and all this stuff. Okay, so we got that one. Then they define the wind turbine output circuit. These are the conductors between the internal component of the small wind turbine, all these, and the equipment. The output circuit of the turbine coming out of the tower. Yes, sir.
Is coming out of the turbine at DC or AC?
AC.
AC. But it's just the way that the turbine's built.
Well, if you put the inverter at the top, an inverter converter at the top, then it becomes DC. But typically, you don't want to do them there. You're going to put them closer to the load. So it's some form of an AC. I hate to say AC because AC to us is 60 or 50 hertz. That's some form of an AC. There are the bigger turbines, guys, they use dual feed induction generators. Dual feed induction generator technology is completely different than this technology. They don't do the inversion. They use induction. Most of the generators that we use is synchronous generators because they're so easy to control the speed. You control the speed of the prime mover, then you can control the frequency. But the wind, you can't control the speed of the wind. You know, it's uncontrollable. So what they use induction generator, the speed, the relationship between the speed of the alternator and the frequency, it allows you to fluctuate so much and maintain the same frequency. So what they do is they use dual feed induction generator, and then this is where they use the grid to actually start that turbine. So the alternator, it's interesting the technology that they use. Inverter, converter, they do their bidirectional street. So one direction, they use the grid to start and control the speed of the induction generator and bring it up to speed. And when it's up and running, it starts pumping current. So they utilize power from the grid to start the alternator. And then bring the power back into the grid. Okay, so this is my wind turbine circuit. We have wind turbine system. This is just defining what a system is, small wind electric generators, and the code defines you were talking about this article 705, so it is a power system that you have to apply all the rules of a power system and bring to a building from marking and so forth. So it's a power system, power generation system. For those, and I apologize, this is a lot technical now, we're getting into a little bit more technical stuff. This article covers the wind turbine, so if there's any, and the NDC code book has tons of other articles, so if there's any differences between this article and the article 300 or article 250 or article 110, this article rules. Typical, guys, for all chapter 6 articles, right? Chapter 6 will modify chapter 1 through 4, typical in NDC code book. And we were just talking about this one. Every time you bring a system in parallel with a prime source of power, you have to adhere to the rule 705, the chapter 705. Long story short, this will tell you, by the way, you have to have a means of identifying the second source of power to the building, number one. And of course, you have to have a means of isolating the power. That power has to be isolated upon the failure of the grid, because you don't want to kill electricians. So that's the anti-islanding is coming directly from 705 for the solar photovoltaic system as well as for the wind. And if you decided to go an explosion proof, you're familiar with the hazardous location, right? All the electricians and engineers here. If you decided to go put this wind turbine in a hazardous location, class 1 div 1 or class 1 div, class 2 div 1 or 2, then you have to adhere to the rules of the hazardous location. Means explosion proof and a bunch of other things. Well, who would go and put your alternator right in a class 1 div 1 location here so you can have an explosion proof alternator or explosion proof inverter converter? So anyway, these are just, I'd like to throw these for them. In 2011, they said, I love what you guys did with the presentation on renewable energy, but I wanted to ask you guys, when you were doing your presentation, sitting there as an engineer, we were ingrained that when you design a system, the system has to be safe. For years, safety was #1 priority. And now lately people start thinking, okay, we want it to be safe. Also, we want it to be economical too. So economy, and that's what I'm waiting for somebody to rewrite the NEC code book from an economical point of view, as well as from a safety point of view. This is written from a safety point of view. To give you an idea, guys, we design a hospital, 4,000 amp switchgear, 4,000 amp switchgear. When everything is up and running, you're lucky if you get 2,000 on the system. Now, what happened to all the copper, all the pipe, all the electrical system that we threw in this hospital? And when everything's up and running, we're sizing for 2,000, maybe 2,500. Talk about economical. Huh? Yeah, 25, keep adding 25% and 25%. By the time you finish, and there's also load diversity, by the time you add the load diversity, meaning it's highly unlikely that every receptacle right in this room are something's plugged into it and running. So you end up, we always say when we design a system, you're lucky after the system is designed and done. You're lucky if your load factor is 50, maybe 60 under the extreme scenario, meaning you have 40% of the system is oversized. So anyway, but there's politics behind it. So because there's politics behind this one, because of the wannabe environmentally friendly people, rightfully so, and NEC code book, remember, territorial here, they want to prevent other people from getting into this business, they added qualified person. So that will give the authority having jurisdiction in Nebraska and elsewhere to sue you or put you in jail if you mess with things that you're not supposed to. And that came, guys, with the solar system and with all renewable energy, because a lot of people want to install the system themselves and so forth. So you have to be a qualified person.
Well, what is the definition of qualified?
The code define it's defined, will define in OSHA as well. Oh yeah, they define it. You have to have the knowledge and the skill of the operation and the construction of the equipment, and have received the safety training to recognize and avoid the hazard.
Still, it's fine.
Well, if I'm the inspector with you, I say, what's your qualification? You went to Dunwoody or any of your technical from the electrical program. Well, I check, right? But you went to a nursing school and have an AS degree in a nursing school. Well, maybe that's not not as good. I mean, yeah, I know it's still vague, but there is and qualification safety. Have you gotten safety OSHA? We have a lot of OSHA training. You're familiar with OSHA training. Have you received your 10-hour OSHA training or 30-hour OSHA training? Have you received training on arc flash that's coming out of DC? Yes, check, no. And all this, guys, happen if you burn a building. Really, you're an architect, you know what happened. All these are pulled at a point when something bad happened. Then when going in front of the judge.
That's fighting right now and saying, well, just because you're an electrician does not mean you know how to fix it.
That's a fight between them and IBW has been, and I think IBW pulled out of it. I believe they pulled out of it and they have their own certification now. So yeah, there's a lot, as I said, there's politics in it too. So that's so if you want to put the system in addition to any electrical system to your building, you have to have a qualified person. And also the inverter, you can't. Were you guys think you were saying that somebody want to build their own turbine? right? You were just saying that. Well, that's how they catch you here. It has to be identified and listed. So you go put your turbine in your farm. I don't think anybody will ask you, but you start selling that turbine or connecting it to the grid. They're going to put yours. You are listing on that. Then the inspector would not allow you to wire it. And I hate this one, guys. As an engineer, personally, I do hate this one because it kills innovation. Regulation always kills innovation. I hate to say it, because it doesn't allow the people. Now you hope go regulate with, getting a UL listing on that. How are you going to compete with all these big boys? So anyway, but that's where safety, they hide behind safety and so forth. So that's a few things. I'm going to watch the time, guys, if anybody wants. So it's 3:03. If anybody wants to change to the next, I don't want to be a captive audience here. Everybody's okay? Cool? Anybody wants to, Mike, you want to flip? Okay, I just want to give you a few seconds here to anybody who wants to flip, to move. I don't want to torture you a little bit more with that one. Before, I want to skip over these and go, just because of the timing, I'll get back into the details. These are a lot of details. Actually, I might be able, so that's your listing, we have time. Diversion load, they define the diversion load installation. The primary means of regulating speed of the wind turbine shall be equipped with additional reliable means, and that's where you get into having that band to control the speed of your turbine, other than the grid. Surge protector, you guys are familiar with surge protector. I believe, I didn't check on that one for the electricians among us. I think 2014, NEC 2014 is coming in next year, right? Next year is 2014, and we in Minnesota, we adopted immediately. I don't know about you guys, but in 2014, I believe they're requiring a surge protective device on the service. It's a standard engineering right now. It's not a big deal. Every project I work on, right at the main service, the 4,000 amp or the 200 amp service for commercial and industrial, not dwelling, you have to have a surge protector. So if you have a surge coming from the lightning or from a high voltage hitting a low voltage line and big jump into the voltage and burn your equipment, that will capture that voltage, take it to Mother Earth. This is what the surge protective guy's job is. There are three types. They say type 3 is usually on the branch circuits, typically right at the receptacle level. Type 2 on the load side of the disconnect. The one that they require, type 2 load on the load side of the service disconnect means. So that's the type that you require. I'll let you guys go. Okay, thank you. So anybody else wants to switch, guys? We're good? Okay. So that's the type that you need is type 2. Now, can I put type 1 there? Yes, you can. You can do type 1, but the required type is type 2. Is type 2. Okay. There you go. They have this one. They allow you to put a receptacle right next to the tower with an overcurrent protection device. Oops. You guys can come in. Are we supposed to stop for 15 minutes or keep rolling?
Oh, I think it was 2:15 the first off, so I don't know if there's another one here.
No, there is not. Wait for a few people or keep rolling. So this one allows you to have an overcurrent protection device, protecting receptacle that you can use for maintenance or collecting data right next to the tower. That's a nice article. Voltage limitation. What's the highest voltage that you can get out of this tower? If you're doing non-dwelling, the limit is the sky. You can get 750 volt. You can get 13,800 volt. I don't see them making it on this level. If you're doing dwelling, you're limited to a maximum voltage 600 volt or less. That's typical also on the solar. You're limiting to a 600 volt or less. Other installation, if you're doing a wind on non-dwelling premises, there's no limitation on the voltage. But if you have, anybody have, the electrician guys, have you guys done medium voltage higher than 600 volt? Anybody? If you go higher than 600 volt, then the equipment have to be listed for high voltage. So what they do is they refer you to this section 9 of the Article 6940, which if you guys go there, it will tell you, oh, by the way, if your panel, if you're generating at 1200 volt, That's higher than 600 volt. Your equipment have to be listed for high voltage equipment, meaning the insulation is higher, and they refer you to a different article that talks about insulation and design and construction for higher than 600 volt, which is bigger equipment, different, a little bit more robust design for it. DC Utilization Circuits, voltage shall comply with 210.6. If you decide to, in the house, to utilize the circuit at the DC level or actually at the AC level, then you can't bring 600 volt and burn a light inside the house, right? There's a limitation on the voltage branch circuits that you can burn a light. A limitation is 122.77. You can go 600 in tunnels for branch circuits. So that's refer you, if you guys go there 310, it gives you a limitation of, can I burn a light at 600 volt in my house? No, you can't, even if you want to, code-wise. If you don't care about the code from Nebraska, like he said, you can do anything you want, right? So that's kind of, now here's an interesting circuit, and they give you maximum voltage. Circuit over 150 to ground. If you're up to 150, that will give you guys 120 to ground and 240. Typical for dwelling, right? 120 to 40. If you go higher than that, like 480, 277, then on a 1 and 2 family dwelling, remember that dwelling, because a lot of people are becoming environmentally friendly when they install this system in their backyard. It has to be accessible only to qualified people. All this equipment have to be accessible to qualified people. It has to be guarded, and the branch circuit also, it has to have some branch circuit limitation. The same thing, the branch circuit limitation on the voltage that you can burn equipment at. You can see, but you don't see anything about commercial industrial. You do commercial industrial, you can, the limit is the sky for that one. And then this is talk about the sizing, guys. I walked you through a lot of these, the sizing. Turbine output circuit, if you don't believe what I wrote on that first slide, that refer you to number 3. If you guys remember that, number 3 says the maximum current at maximum power output, which is 25 miles per hour, I believe. So that's how they define the turbine output circuit. Inverter output, maximum output current shall be, the inverter shall be considered continuous. Remember that 125, that magic number, that's where you get you 125. Standalone system, input circuit, maximum input current shall be a standalone continuous inverter input. So dividing the continuous inverter input current rating of the inverter producing rated power at the lowest input voltage. If you have a standalone, they want the maximum current has to be at the lowest voltage, because the lowest voltage in a power system produces the highest current, right, in any power system. So they get into, and who cares here, when you size your conductor, if you remember 1.25 times the Imax, that's where the Imax is defined for all these systems. Imax is defined for all these systems. Small wind, they tell you very clear, it's continuous load. We're familiar as electrician, guys, what do you do with a continuous load? 1.25 to size conductors, and for the most part, 1.25 to size overconduction device, with some exception for motors and HVAC equipment. These are straightforward sizing, sizing 1.25, like we said, for these circuits. Do you guys remember what these are? These, if you, for the electricians, again, these are a little bit too much into the detail. If you end up with a non-standard overconduction device, then you can't go to the next standard. For example, if I have, this is where you can get a 500 kcm conductor to feed a 400 amp panel. Even though 500 kcm can give you 380 amps, so what happens with the 20 amps? Exception in the code, that's exception B, where it tells you, no problem, as long as you don't touch the ceiling of 800, you can, your overconduction device can be slightly higher than your conductor. So they are saying the same thing, this will apply to it. I don't know how many of you guys are familiar with 100% rated circuit breakers you guys installed. If you dealt with anything 1000 amp or higher, you're probably familiar with something called 100% rated circuit breakers. Circuit breakers cannot, by design, produce more than 80% of their rating. So when they tell you you have 100 amp in your building, in your house, you really have 80 amps. They can't produce more than 80% of them. Now, when you get into typically higher than 1000 amp, they become more robust, bigger, typically power electronic trip circuit breakers, and they rate them They can, they don't have to, but typically they rate them for 100%, meaning when they give you a 4,000 amp power circuit breaker, it's rated for 4,000 amp. Pull the 4,000 amp out of it. Never seen a system that pulling 4,000 out of it and stay running. So that's what this tells you. So what they're saying here, guys, all these equipment need an overcome protection device. All this from the turbine output circuit, inverter output circuits, storage batteries, they need to be protected from overcome protection device with some exceptions. If you're connecting to more than one electrical source, shall have an overcome protection device so as to protect you from both sources. And my understanding, if you have the inverter that goes bidirectional, you have to look at protecting conductor from the power coming in from the grid into the turbine to start and utilize the turbine, or vice versa, or from the turbine to the grid. So that's a few things about that one. There's the possible backfeed. So that talks about backfeed, and where you have to have consideration for overcome protection device if you can backfeed the equipment. And this is where some of small wind electric systems rely on the turbine output circuit to regulate the turbine speed. What they do is they sense the output, take a sensor on the output and feed it back into the controller of the turbine to regulate the speed of the turbine.
So it doesn't spin too fast.
Yeah, some type of and there's also a switch where you can shunt the system, bring it to a halt, complete halt. So this is where, so inverter may also operate in reverse for turbine start up and speed control. That's where they talk about speed control in reverse. This is very typical for also bigger equipment. I've seen I've never installed them, but I've seen a lot of system guys that where it goes both ways. You know, you take the power goes from the grid to start the turbine, and after the grid is started, it takes it back into into the grid. So if you are to do any of these, if you're using the output as part of regulating your speed, then you have to pay a lot of attention to even the disconnect, having a disconnect for the turbine, because you disconnect the turbine, and the turbine output is controlling the speed of that turbine, you will overspeed and burn equipment. And all these will be, that's what I say, the devil is in the details a little bit when you get into the regulations.
So when you buy a commercial turbine, a lot of this is included in the design of the turbine, right?
Yep, the turbine, yes. You mean the 2 meg and the 3 meg and
well, the manufacturer of the turbine takes all this into account, and all of these systems are in the turbine already when you buy the pre-designed turbine.
Yeah, you probably need a disconnect. You need to provide the major ones that.
No, I mean the ones about controlling the speed.
Yes,
that's all in there.
Yep, absolutely, absolutely.
Okay.
Absolutely. Otherwise, they're not going to depend on you to put a disconnect and take the output of the disconnect and feed your equipment. Absolutely. Or if you put your disconnect, it will be after the feed. After you put your disconnect, after you tap the power. You know what I mean? So if you're disconnecting, you're really not disconnecting the power going into the control circuit.
Okay.
So a transformer, if you guys are familiar, this is typical when you have a medium voltage system. You take the power and you convert it into a higher voltage to drop it on the grid. If you do that, then you have a primary and secondary transformer, right? And the primary, so you have a transformer that's primary and secondary. Where's my, so here's my, so you're going here and you're bringing your output in here and you're dropping it to the grid at this point. So now, when you do that, when you size your transformer, now this is, I know this is a little bit more details, then you have to consider this is the primary and size the overcome protection device based on this, the primary, when you're pulling power this way. Then if the power is going that way, that will be your primary. So you take the two scenarios when you size your overcome protection device. And 450.3 will tell you 1.25 if it's no secondary here, and a bunch of other rules. So And this talks about overcome protection device used in DC portion shall be listed. Overcome the arc that's coming out of the DC circuit is bigger, so it has to be listed for DC. And again, you have to have the voltage and the current. You have to have the voltage and the current for that equipment. And then moving into now that's basically for all the system. This moving here, guys, is in a standalone system. What happens if you have a standalone system? You don't have a grid. Then they're telling you everything that we said so far. You have to apply the same rule. Wiring on the supply side of the building, there is no supply. You are living in the boony land and you have a standalone system.
There's another group out here that's supposed to hear the same session.
Oh, okay.
They're supposed to start over with this group.
Oh, serious?
Well, that's
I thought, okay, you can bring him in. Okay. Same thing? Oh, boy. Okay. Well, thank you, guys.
One more thing, if I could. After the,
Yeah, absolutely. Yeah, absolutely.
how much space, I'm an architect, so how much space is taken up by the inverters and all the equipment other than the turbine up on the tower? First of all, about how much space am I gonna need?
4 by 4 feet.
Okay.
6 by 6 will be, yeah, absolutely. Yeah, I will take, no, I'll take a second here. I'll take a second. Okay, thank you.
So 4 by, that's relatively.
That's really, yeah, for that particular system is really very small.
This